Okay, it looks like we are about to start. Okay, I see the party was good yesterday. Let me tell you one story. When I was a small kid, I really wanted to be a comedian, but people laughed at me. But guess what? No one is laughing now. Okay, so welcome everyone. My name is Grzegorz Piwowarek, and today I will show you what Hazelcast actually is. Quite a common pattern is that whenever you see some discussions happening online, or some people speaking, during the hallway track, and when the name Hazelcast is brought up, usually someone is like, "Oh, Hazelcast, that cache," or sometimes even worse, "Oh, you mean that Redis clone," or something like that. And that was true for some long time ago. Hazelcast used to be just a cache, but it provides way more than that. And I used to be a Hazelcast user myself before I joined Hazelcast, and even myself was quite surprised with what I managed to find in the product after spending some time digging into its internals. So let's get ready. By the way, you can find my articles on forcomprehension.com. I do some trainings, and you can find me on Twitter. The story of Hazelcast begins in 2008 in Turkey. And indeed, that was a simple caching solution. So it was just a set of convenient distributed implementations of Java interfaces. And that's pretty much all. But over time, it grew into something way more than that. It's not a cache, it's an IMDG, or in-memory computing platform. But even now, since 5.x, it's not even IMDG on its own. It's something more. So over time, the number of APIs grew. We developed a binary protocol for our clients, which enabled polyglot experience. It's no longer just a JVM tool. You can use Python, Golang, or C++ to interact with it. But what's more, on the side we were developing another product, stream processing, and we managed to combine them both into one single product experience. But even besides that, if you look at the number of functionalities, APIs, data structures, it's still way more than just a map or just a cache. And the common awareness is that it's pretty much a distributed map. We grew some quite impressive number of clients, mostly working in insurance and finance. So you can see logos like Apple, London Stock Exchange, Walt Disney on the list. And quite a huge number of various tech integrations out there. So now, let's try to decipher what that IMDG actually means. So it states for in-memory data grid. And those are what this effectively means. In-memory means no persistence. And the main property of when you say that you are doing something in memory, usually it means it's orders of magnitude faster than if you'd be working with with your old school hard drive. So that property suggests that all kind of processing that's done inside the Hazelcast cluster will be pretty fast. Way faster than if you would need to flash everything to disk each time. The data means that, as you could guess, that's storage of data. But besides that, you can do some computations on top of that. And this is where it becomes really interesting, where you actually get to run some computations on top of data that you have already in the cluster. And grid is simply multiple processes working as a group. You can think about it as a cluster. And Hazelcast started as an embedded solution. You just started within your Java project, but we also developed the client-server topology, which is actually one of the which is the main one, mainly adopted in production running systems. So, if you know this already, let's try to think where can you actually squeeze Hazelcast in your architecture. So, if you think about the Hazelcast as a cache or just some in-memory store that's supposed to carry hot data, fetched, for example, from a database. So in your architecture, you would have probably your data store or some other source of data. You would have a Hazelcast cluster. And how do you orchestrate? How do you put data? How do you take them out? So an easy use case. So you write an if-else, right? You check if something is in Hazelcast. If it's not, you go to a database. And if it's there, you pull it, then add it to Hazelcast, and it becomes complex. It's a bit worse the other way around. If you try to add data first to the Hazelcast, then to a database, but guess what? You have a distributed transaction. If something fails, you could end up with data being in Hazelcast and not in database. So as you can see, that's a simple problem, but generates difficulties. So there are a few cache access patterns that exist, which can kind of help you think about this a bit differently and avoid that. The first simple one is a read-through. In such setup, your application doesn't talk directly to a data store. It can, but doesn't need to. Because if you reach Hazelcast directly and the data is not there, the Hazelcast will reach out to the database on its own, backload this data, and then return it. So as you can see, that's a bit simpler. If you can do a read-through, obviously that's a bit slower than reaching directly to a database, but only the first time. Every next access of the data of that particular entry will be fetched directly from a Hazelcast data store. So if you can read through, you can probably write through as well. So if you write new stuff to your data store, but write direct to Hazelcast, Hazelcast with the properly configured map store will actually do it for you. Again, this will be a bit slower than writing stuff to a database by yourself. But if you really care about lowest possible latency to squeeze out of that setup, you could make that write to a database asynchronous and periodic, which means that you write something to a Hazelcast very quickly, but you don't get the guarantees of having it flashed immediately to the data store. You get some latency for the price of loosening some guarantees. Which one is the best? I can't tell you. It's all about understanding the trade-offs and picking what's right for you. By the way, if this low latency is not low for you enough, and you're even a bit more okay with loosening those eventual consistency boundaries, you could go for something like a near cache, which means you put a cache into a cache, or rather, not in a cache, but on the client side. So if there is data that you access frequently and you don't want to pay the network trip price for that, you put it into your client directly. And if there are some invalidation messages, and Hazelcast will be also used for sending invalidation messages to other clients as well. And guess what? If you want to use it as just a single artifact, one entry in your POM XML file will get the job done. For a very long time, we've been running that policy about zero dependencies. That's obviously not 100% zero, because you have some external integrations, which are mostly optional. And obviously, we didn't rewrite Jackson and Snake YAML by ourselves, so we shaded those. But if you add this artifact, you get certain guarantees that you won't end up with a lot of mess on your class path. However, it's quite likely that we will abandon this in the future, since it turns out that the jar file is not the main distribution anymore. The Docker image is. So, and now, if you would like to run it in embedded mode, you call that simple methods. It's Hazelcast new Hazelcast instance, and you get, guess what, Hazelcast instance. If you want to run it in a client server, well, guess what, you call Hazelcast client, new Hazelcast client, and you get Hazelcast instance on the left side. So technically, if you'd like to migrate from embedded to client server, at least from the point of view of compilation, it's just a matter of switching the implementation. Obviously, it's a bit more complex than that, but at least your code will compile since the beginning. When it comes to support for other languages, you get JVM stack, C++, C#, Python, Node.js, and Golang. There were some discussions about Rust, but I can't promise you if that's going to happen and when. Okay, let's try to use it then. So you create a new Hazelcast instance, you fetch a map, you put something inside, you get something inside, and you get the value. Not that impressive, right? By the way, you can swap this IMAP with a Java map, and it will work as well. Anyway, that's not very impressive, right? You put something, you get, it works, right? But what's actually happening underneath, if you use the default, the base, IMAP data structure, is that the data is actually partitioned. It feels like you are working with a single map, but actually the data is partitioned among various nodes. This data is not only partitioned, but each partition have a backup. So then backups will be placed on other nodes as well. And this is just the beginning, because so far we covered basic cache and key value map functionality, but that's where the fun begins. Besides map, you can find many other data structures. You can find data structures like a multi-map. You can find a structure like a replicated map, which is just like map, just it's not partitioned, it's replicated. Whole map is being replicated. You find set lists, but the most important, quite interesting, is that you can find also queues and topics. We won't replace your Kafka. We are not claiming that we won't replace your RabbitMQ. But if you care about, if you have your Hazelcast deployment already, and you want to do, for example, a simple notification mechanism, this is probably good enough for you. But data structures is also just the beginning. Because now imagine, so let's go back to this simple example with the code. So you put some data, we get it back. Now let's say we want to process some data. So how would you do that if you had a Java map? You would probably go entry set for each and just go through that. And that would work. Okay, but now it gets a bit more complex. If you're probably running your Hello World project, that would work for you just fine. But imagine you have a production deployment. You have 50 nodes. You have dozens of terabytes of data. And suddenly when you do, for each on a map to process all the data and then put them back into a cluster, suddenly it's not that easy. Probably you will run out of your RAM memory on your machine. So this gets tricky. This is why the best place to actually perform that computation is Hazelcast cluster on its own, or rather the node that's owning a particular partition. So if you want to process all the entries in your map, there's no need to pull them all to your local setup, do the computation and put them back. You can deploy your own implementation of an entry processor, which will do this all for you in a thread-safe fashion as well. But if you can do this kind of processing, why not go a bit more generic and provide capabilities of running pretty much arbitrable implementations of runnable interfaces? That's an option as well. Okay, so we know how to process data. We know how to run something on a cluster. But what if we want to compute, let's say, some aggregations? So imagine you have a map with your employees inside, and you want to get one question answered. How much, let's say, do their all combined salaries cost? So entry processor won't help you here, but an aggregation will. So there is a way to offload the whole operation to the cluster itself and just return and get the response back. The same for simple queries. Maybe you don't want to return all your employees, but only a small subset of them. What do we do then? By the way, all those operations seem kind of similar to what you would have on a database, right? Basic aggregations, filtering, select, asterisk, where something. And that's the case here. So since 5.0, we introduced a basic SQL support, and the goal is to be able to get rid of all those Java-specific implementations and replace everything with SQL. The basic support is already there since 5.0, and in each subsequent version, it will be improved. We want the SQL to be one of the main APIs in the way how you interact with the cluster itself. Okay, but now we need to refresh our knowledge on one important topic at CAP theorem. Because we need to understand what guarantees does Hazelcast provide. CAP theorem is the basic constraint of the distributed systems. It effectively means that if your nodes can't communicate, they can either answer something that's potentially outdated or not answer at all, or give inconsistent answer. I mean, give you inconsistent answer or not answer at all. Because the network is unreliable. So it's always peak 2, but in the world of distributed systems, network is always unreliable, so you always get to choose between AP and CP. The Hazelcast itself is an AP system. It prefers availability over consistency, but there is a way to designate a subpart of the cluster to work in a CP fashion. It's called CP subsystem, and it provides a slightly different set of distributed primitives to work with. If you've been to Andrew's talk yesterday, he actually brought it up while talking about Raft and Loom. But there are restrictions. If you want to use that, there needs to be at least 3 members. Because if you have 1 member, there's no distributed system. If there are 2 members, they can't outvote each other. But if there are 3, 2 can outvote at least that last one. And in that CP subsystem, you will find tools like semaphore, countdown ledge, atomic reference, atomic long, and we are also working on the leader election as well. But that's also not everything. There is more than that. There are also advanced data structures, like ring buffer, which is, by the way, used internally by our topic implementations. Ring buffer is a kind of a data structure which is like a circular linked list with a fixed length. So if you go over the length, the oldest elements will get overwritten. Another really cool and interesting one is HyperLogLog. So imagine you have this really big cluster. So you have this 50, 100, 200, just a lot of nodes. Just pick up your number, and a lot of data. And now imagine you want to figure out the number of unique elements of the data set. And imagine that with that huge volume of data, you are, for example, in a very big company, e-commerce company, that's processing, let's say, click streams that user generate. So in order to give you a precise answer, you would need to pretty much freeze your whole cluster for a second, collect all the data, and return it. And that would go out of date pretty much a millisecond after that. So there is no point on doing that, but you can get an answer that's incorrect, but with a very small margin of error if you are doing this for big data sets. And this is where HyperLogLog will help you. Another interesting thing is a flake ID generator, a cluster-wide ordered unique identifiers, which you can use out of the box. There are trade-offs between various ID generation strategies. If you go, for example, for a classic, monotonically increasing sequences, there can be performance impact because you need to have a single source that will provide you those. Secondly, it's very easy to enumerate your resources. So, for example, if your API is public and attackers see that the access that let's say your clusters have IDs with increasing, it's very easy to guess the next one. On the other hand, you could go for totally randomly generated IDs, but those are usually unordered. But Flake ID gives you kind of both. It gives you both ordering and uniqueness. If you don't have the CP subsystem configured, you can still get atomic long-like semantics just by relying on CRDT PN counter, which is a conflict-free resolution data type. It doesn't require communication to be able to work correctly. So even if you cut the wires between all the members, it will all work as intended and will give you a correct answer when you ask for it. And those are basic data structures that you get out of the box from Hazelcast. But there are also integrations that you might be using Hazelcast without even being aware of that. Well, there's a small chance of that, but it's possible. So, for example, we have that Hibernate second level cache integration. This one probably, if you are using it, you probably know about that. But there are two interesting flavors to that, because you can use Hazelcast map as a storage for your entities, and that's pretty intuitive and obvious. But you can get to quite interesting properties if you use the other setup, which involves actually storing data in a caffeine cache. And you might be thinking, Grzegorz, you have Hibernate integration, and you tell me that in one of those integrations you actually put the data in a caffeine cache and not in Hazelcast. What's the point? The trick is that in such a setup, you use Hazelcast as a messaging tool, pretty much. So the data is stored locally in caffeine cache, but the invalidation messages are being broadcasted over our messaging utilities. So the data is local, the access is very fast, but if you evict something, this will be also evicted from other instances of that cache connected to the same Hazelcast cluster. If you are a Spring fan, if you don't like SQL, you can use Spring data to interact with the Hazelcast cluster itself. And this feels pretty much as standard Spring data JPA, where you define your interfaces, and instead of writing SQL, you write very descriptive method names, and the rest is auto-generated for you. Another very interesting one is the Quarkus Hazelcast client. And you might be thinking, Greg, but Quarkus is another framework. How exciting can this be? You know, you probably you did a few lines of code that's responsible for auto-configuration, and that's all. That's not the interesting part. Quarkus provides support for GraalVM, and it's not just an afterthought. It's been built with GraalVM in mind. The same applies to all the integrations, at least those officially supported, which means the Hazelcast client actually can work on GraalVM, which is pretty cool. It was pretty complex to do that. Another quite interesting one, and this is the one that you might not even be aware of, is that if you have multiple, let's say, Tomcat instances running, and you want to have your HTTP sessions being shared between all of them, you will need some form of distributed storage. And Hazelcast has a plugin directly for that. So if you create a HTTP session while interacting with one Tomcat instance, and then let's say another request gets round robin to another one, this HTTP session will still be present there. So your client won't experience any difference. Another tool, Apache Shiro, which is provides a bit similar concept, but it provides quite a lot of cryptographical tools on top of that. But that's not all. If you try to use Hazelcast locally, you will see that it's pretty convenient. So you start a few instances, and before you even notice that, whoa, the cluster is formed. You didn't need to configure at all, but your cluster is formed, and you can play with that. This gets a bit more tricky if you go into the cloud, because auto-discovery strategies, they work slightly different there. But we have plugins for 3 major cloud providers: AWS, GCP, and Azure. So if you deploy your own Hazelcast into the cloud, they will also auto-discover. Nodes will be able to auto-discover themselves based on some cloud-specific strategies. But running Hazelcast in the cloud on your own is one part of the story. On the other hand, there is Hazelcast Cloud. which means that it's not you who is running Hazelcast in the cloud, but us who is running Hazelcast in the cloud for you. And we have two flavors of that. One of them is we call the so-called enterprise dedicated offering, which is pretty much Hazelcast in the cloud, just on our side. But we are experimenting with a new product which will be released soon. I can't really tell you when, but I would bet on next month. Concept of Hazelcast serverless. Because Hazelcast gives you quite a lot of tools, but still gives you quite a lot of choice. So you need to figure out how many members to pick for your workloads, what machines those members need to be running on. You need to fine-tune how many backups of each partition do you want to have. Do you want to have those backups synchronous or asynchronous? Should you enable persistence, hot restart store? Should you use on-heap, off-heap store? There are a lot of things to think about when finding your perfect setup. And the idea of Hazelcast serverless is to take away from you all those worries. So you will be thinking only about the data that you want to process, and everything else will be done on our side for you. So there is one slider, you choose how much data you want to process, and the rest is on us. More details coming soon. But that's not all. If you are a very big client, you're interested in a bit more advanced tools. So for example, imagine you are running your production workload on one cluster, but imagine something can go wrong. Something goes wrong. And what happens? Your Hazelcast client doesn't connect to a cluster because someone cut off the network cable to a very important data center. So perhaps your company is not okay with that kind of risk. So this is where automatic disaster recovery failover comes into place. You provide an alternative configuration for your Hazelcast client, and it's able to seamlessly switch between the main cluster and the other one, which is used as a backup. So that you think about it as a kind of active-passive setup. But if you have multiple data centers, let's say all around the world, let's say that you have some in Paris, some in Asia, San Francisco, Africa. You might be tempted to actually spawn this huge cluster consisting of hundreds of nodes from various continents. And as you can guess, as the number and as this distance between them increases, as the number of nodes increases, it gets a bit more heavyweight and can get flaky. It would make a bit more sense if you create separate clusters for each of your data centers, and if you want this data to be synced, you introduce one replication between them. So each cluster is a separate entity, but they replicate data between themselves according to your configuration. By the way, this feature can be also used with the disaster recovery. So it's perfectly fine to have one main cluster, another one just uses disaster recovery, and then one replication configured to actually backport transfer all the changes going from the main cluster into your backup one. This can be also, sometimes clusters go out of sync and you want to trigger it manually and ensure that they are eventually in sync. So you don't need to be worried that suddenly you need to transfer terabytes of data. The one replication is smart enough to be able to identify the difference between two clusters and send only the relevant parts. It might appear that if the Hazelcast by default is storing all the entries in the Java heap, it might not be good enough because the garbage collection is there. So if you are looking for a bit more predictable latency, you could use our off-heap store, which is called high-density memory, which means that all the entries are actually stored outside of the area of the garbage collector's jurisdiction, and it gives you a bit extra latency points. But if we can store our data already off-heap, we also implemented basic support for persistence. It's not a like real database like persistence. It's just an utility that assists you in a few scenarios. So imagine you are running this, you have a huge cluster, I don't know, 550 nodes, and you want to upgrade all of the members. So what you need to do, you do this rolling upgrade. You need to stop one, you need to pretty much upgrade it and start it again. When the node disappears, cluster notices it, and it has some non-zero impact on that, because it needs to figure out what to do with the partition if they need to find a new owner of a partition or not. But hey, then and cluster might be able to figure it out, but then okay, that node comes back in, and the data is repartitioned again. And if you do this, let's say n times, that's a bit suboptimal. So if you use the tool, the hot restart store, the basic persistence support, what it does actually is that before a node restarts, it dumps all the data to a disk, and then it restarts and reads them back, and reappears pretty much instantaneously, which avoids any kind of disruptions. By the way, we are further evolving the persistence, so in the future, we are planning to introduce a tiered storage, which means that some part of the on-heap storage will be offloaded directly to a disk. It's an option that you can choose. And this is where the fun part starts. So far, we covered pretty much just the basic IMDG features, but that's not everything. In the past, at the site, we were developing this Hazelcast Jet product, which is a real-time stream processing engine, which is capable of, just processing, like taking data from various sourcing, processing them, and also syncing them into pretty much anything of your choice. Some people thought that it was just for Hazelcast data, but no, your sources can be whatever you want. And if you've been yesterday to Andrew's talk, you learned about basics of the project Loom. The fun part is that the core of the Hazelcast Jet is also Loom-like solution. But it, as you can guess, it was implemented a long time ago when no one was dreaming on Project Loom being, introduced to the JDK. So actually inside the Hazelcast Jet, we have a similar solution, and it's all described in that white paper. And if you want to learn more about performance and examples, those are two links that you should have a look at. You will fully have access to that in the slides at the end of the presentation. So we have this Hazelcast product, IMDG. We have Hazelcast Jet, which is a streaming solution. The interesting part is that Hazelcast Jet depended on Hazelcast internally. So all the it would use it as a state storage, as a metadata storage. So if Hazelcast Jet depends internally on the Hazelcast itself, it was a kind of no-brainer to put those two solutions together. So since Hazelcast 5.0, it's not IMDG and Jet, but this is just combined into one single product, which gives you not just real-time stream processing capabilities, but also opens up a new, quite interesting enrichment opportunities if you have, if you rely its IMDG utilities. The way it looks like, if you'd like to try to define your own pipeline, that's pretty much an example. It might look like Stream API, for example, but it's not really it. It looks like it, but it's not code that just runs, but it's a pipeline definition that gets uploaded to a cluster and then executed. To sparkle some ideas into your imagination where something like that could be used, imagine you're a GSM provider and you noticed and you're analyzing how people are moving. So for example, in real time, you are processing, you are seeing the SIM cards connect to which BTSs along the way. And in real time, you start seeing patterns. you see that that particular person is switching to BTSs closer and closer to the border with Czech Republic. Okay, so that person is probably going abroad. And if that person is going abroad, perhaps they are disorganized and they forgot about the buying, enabling the roaming package or getting extra gigabytes of transfer. Let's send them a text message in real time right now. And those are cool opportunities that you get when you combine those two things together. If you'd like to see more examples in action, we have the whole repository with Hazelcast Jet demos. And if you look at first two, there is Bitcoin, dev cross, and cryptocurrency sentiment analysis. Quite relevant nowadays, isn't it? So if you want to learn more about the jet itself, quite a lot of information is public. So the architecture and the design documents were open sourced, so you can just go and read about the design decisions that needed to be made all along the way when developing it. So, as you noticed, today I didn't give you a lot of practical introduction to Hazelcast. If you want to get practical introduction to Hazelcast, there are better places. For example, training.hazelcast.com, where for free you will get quite a lot knowledge. Well, technically not for free. You need to hand over your personal details, but you get a couple of hours of hands-on study. And that's pretty much all that I wanted to show you today. I hope I managed to spark your interest in the Hazelcast product. I hope you learned that it's not just a cache, and I'd love to see you try to use it. Thank you. So here comes the question time. Give me a second. That's more difficult than it looks like. Give me a second. That's really way harder than it looks. Okay, here we go. Okay, it works. So there are a bunch of questions. How to handle model changes with canary releases? Okay, it's a good one. The main, since 5.x, the main serialization protocol that's advised to use, we call it compact serialization. It's pretty backward compatible, so you can easily evolve those models. Technically, on the client side, you use a Java model, but internally it's represented as a generic record, not as a Java type. And if you're doing canary releases, you probably still need to think about how to do it in backward compatible manner. So those are two versions of a particular class, which are backward compatible. That's perfectly fine. There are no problems with that. If they are not backward compatible, then we have a problem. Okay, actually, I don't see the question on the smaller screen. How to optimize memory usage size of a map? What is the recommended fast and optimal serializer? Is there a better choice than Creo? Generally, when it comes to serialization, I pretty much answered it when answering the previous question. We don't actually support that protocol. We support our own. We call it a compact, which is pretty good and pretty convenient to use. It requires zero configuration and it's optimized for Hazelcast. And in the future, internally, it will be able to do quite a lot of magic based on that. What's important is that it supports partial deserialization. So if you imagine now running this entry processor, which actually processes only one field of quite a complex object, there is no need to pay the price of deserializing the whole object. You deserialize only the relevant field and change it and update it. how to optimize memory usage size of a map. Usually you don't need to worry about size of a map because it's potentially it's unbounded. But I assume you are asking about the size of a cache. So because if you go for the caching solution, probably you want to have some strategies for evicting data, and those can be based, on how long the data was stored in the map, when it was last accessed, or maybe the size of a map. There's no really good and universal answer to that. It really depends on your particular workloads and on your data, what makes sense in your context. In some contexts, it doesn't make sense to keep data longer than some time. And in some other workloads, it doesn't make sense to keep more than a certain amount. Usually, it's always a good idea to keep some cap on the size. There's a lower chance of getting some surprises running out of memory, but there's no direct answer, easy answer to that. Probably the most obvious questions: what advantages does Hazelcast provide over Redis in terms of pure cache functionality? Okay, I expected that question. If you look at benchmarks and look at the multi-threaded Hazelcast architecture, you will see that actually it performs a bit better. It's also way more convenient to use. If you try to use Hazelcast, if you try to interact with the client and the server, it's way easier to use for Java people especially, due to auto-configuration strategies, smart clients, and I think those are two main things if you look at just pure caching perspective. But remember, we are trying to be something more as a cache, more than a cache. Another question: may I consider Hazelcast Jet as an alternative to Apache Spark? Yes, absolutely. In my project, we are using on-heap memory cache. We decided to go this way since we have strict timing requirements. Read the next due to limits on Slido. I love this one. We saved a lot of time on deserialization of heap cache. Thus, Hazelcast requires deserialization while reading data. Wait. There are multiple serialization protocols, and I'm not sure I fully understand. You can avoid deserialization if you really need to, because if you perform some computations and if you use compact serialization, you avoid deserialization of data that's actually not needed. So deserialization is minimized as much as possible. Do you have some kind of free tier on Hazelcast Cloud and Hazelcast Serverless? Yes. So if you go over to Hazelcast Cloud, you will be able to use it for free. I don't remember exact amounts, but there's some spending. And serverless is not released yet. I can't really tell you what exactly will the conditions be, but yes, you will be able to play with it for free up to certain workloads. Is Hazelcast Jet a commercial solution? Hazelcast Jet it doesn't exist on its own anymore. But Hazelcast 5.x, 5.0, 5.1, they are open sourced. They are open sourced and you can use it right away. There are obviously certain things that if you want, you need to pay for, but the basic version of the product is available for you to try right now. Are there any improvements to evolving data models, different versions of objects in the same cluster, and related to automated serialization that could handle that? I'm not sure if you are, because either any improvements to evolving data model, so I'm not sure what's the baseline here, what we are improving this against, but then we have a few serialization protocols, so I'll go back to the compact again. If you, for example, add a new field to an object, and if you try to store it, that's not a big issue because it can be represented as a null. So we have backward compatibility, but I am not sure what else can I answer here. Okay, that's all. Thank you very much. I'm here during the whole day, so if you have any questions, you can grab me or Jakub over there. or Andri somewhere here, they will gladly answer you and to help you with the same thing. Okay, thank you.